Internet's working. Okay. Let's go over a couple of these questions, guys.
Sounds good.
So
12 and 13.
Yes.
let's get started.
Oh, this conversation's going
So let's go over one of these questions that says so the plan of this week is we're gonna have a quiz on Wednesday, and then our test on Friday, because this is the last problem set in our little unit here. Anyway, so 12 says you're driving your car in a straight line, and your position. So we're gonna go over 12 here. You okay, George? Yeah. It says you're driving your car in a straight line, and your position function is given by this. So again, like we know how to graph that, but that's what the graph would look like, shifted over one. And of course, it's saying it's only defined for t values greater than or equal to 1. Now, there is an interesting consequence of that you might realize as we're going through this. You might go, wait a second, something fishy there. I'm curious to see if anyone will pick up on that. Anyway, it asks, at what time will your instantaneous velocity be equal to your average velocity over the interval from 5 to 50? So say, this is not to scale, of course, but say this was 5, and this was 50. The question's asking, there's some average rate of change over that interval, and what was the time at which your actual speed, your instantaneous speed, was equal to that number? So this question itself makes sense?
Yes.
The way it's worded? Sort of, kind of? Okay, so, well, if it's still a little, maybe let's back up a second. Is the car traveling this curved path? Is this describing a car going around a turn? No, it's not. The car is moving along an x-axis, or I guess a p-axis, a position axis. So, of course, there is like an origin, position 0. At what time is the car at position 0, by the way?
1.
Time 1, yeah. So when the clock is at 1, which is the smallest time value allowed. And what do you think the car is doing as time goes on? Is the car speeding up or slowing down? Slowing down. Because look at the slopes. Slopes are pretty big at first, but as you move to the right on the curve, the slopes get smaller and smaller. So this car is just traveling this direction. Here's the car. So traveling that direction, but it's slowing down the whole time. So we might ask the question, well, where was it at time 5? So what was the position of the car at time 5? What's the answer to that? 12, so position 12. And then I might also ask, what was the position of the car at time 50? Everyone's okay with that, right? No questions there? So graphically what that looks like is at time 5, it's the time axis, is the position axis. At time 5, the position was 12, and then at time 50, the position was 42. So obviously my picture is not to scale, but that's okay. So what I can do with those numbers is get the average velocity. So how do I calculate the average velocity?
Changes x or changes t.
Exactly. So the change in the position over the change in time. So okay, so how far did he move? 45.
No.
42.
Well, that's where he ended up. So he ended up at position 42. So on my number line here, this is where he ends up eventually. But if we're looking at the time interval from 5 to 50, I need to also look at where was he at time 5. So he was at position 12. So On the time interval we're talking about, does this make sense to everyone? How like this is what we care about?
Mhm.
So he was at time 5, he was at position 12, and at time 50, he was at position 42. So his delta x, his displacement, is going to be 30. And the time period is 40. Oh, that's not where your 45 was coming from. So that, of course, is 2/3. So do we feel okay about all that stuff? This is maybe a little bit of review, right? Average rate of change.
What's the units?
What?
What's the label?
Oh, they never specified if they're talking about miles or hours, so we can just maybe say like, I guess if they don't say, you can just assume it's units per second.
Okay.
But okay, so not
That's asking for them? Is that asking for the average velocity?
we're not done. Just to be clear, yes, we're not done. We just basically finished half the problem. So the problem was asking, at what time? Does it make sense just sort of intuitively that there's some spot between 5 and 50 where the actual speed, like the tangent line, is the same slope as the average slope?
Yeah.
So that's what we're asking to find is at what time. Does it also make sense intuitively that he was going faster here than he was going here?
Yes.
Okay, so he was going pretty fast and then pretty slow. And so at some point, his speed was exactly 2/3.
Cooper, can you take that off?
Thank you. Okay, so then what do we do? I used up a lot of room here, so let me go back a sec. Equals what?
The 6 times.
Very close, very close. So if the question had said something like, when is the position equal to 2/3, we would just set that equal to 2/3. But it's asking, when is the velocity equal to 2/3, right? So what do I have to do? If I have a position function and I want to know something about the velocity, take the derivative, right? So my velocity function, what do we do here? What happens if I have 6 root u? What's the derivative of 6 root u? Yeah, so if you can get directly to the answer, good. Yeah, that's correct. You might go, well, I know how to take the derivative of this. That's one I know pretty well. So it's just going to be 6 times u prime over 2 root u. Now, of course, 6 divided by 2 is 3. And so your derivative is going to be 3 times u prime over root u. Is everyone okay with that? We're still fine with that? Okay, so what's u prime, though, for this type of function? It's just 1. Yeah. So it'd be 3 times 1 over the square root of u. Okay. And so there's my velocity function. So what do I want to set that equal to? 2/3. Yep, 2/3. If you're taking the AP exam, you would get a point for just writing this, or you might get a point for writing. Probably write this to be extra clear. You'd say, which is a lot. A point is a lot. A full free response question that you're supposed to take 30 minutes on is maybe 9 points. So get a point for that's pretty good. Anyway, so you're saying I'm going to set my derivative. Now again, those are the same thing. The derivative of position is velocity. So what I write is 3 over root t minus 1 equals 2/3. Right. Did anyone figure out the weirdness?
No.
So what do you guys think?
There's no time zero. Are we like?
That's okay. I mean, yes, that's a good point, but it does specify that this is the position function for only defined for times 1 or greater. The funny business is, what do you guys think the velocity is at time, like right after the time starts, like right at time, like say 1.00001.
Is it?
It's going to be enormous. Yeah, it's going to be. So this car's initial speed is greater than the speed of light, which is kind of funny, but zoom, yeah, rolling cold.
Back to the future.
So anyway, just kind of a funny artifact. You get those sometimes in these math problems that, where they're not entirely realistic sometimes. So, okay, let's solve this. Is everyone okay if I do 2 steps at once and kind of cross multiply and get 9 halves equals this? I can show the intermediate step if we're confused, but you okay with that? So the 3 gets multiplied up. This expression gets multiplied to be with the 2, and then we divide the 2 underneath. So kind of like 3 steps at once. And then what do I do from here?
Square.
That's square root.
Square.
We're going to square both sides. Yeah, because I don't want that radical to be there anymore. So I'm going to square both sides. We get 81 fourths equals t minus 1. And so the time that I'm looking for would be 85 fourths. If I just add the 1 over, right? 1 is 4 fourths. So add 4 fourths on the 81 fourths, we get 85 fourths. Now in this context, it might make sense to write that as a decimal. So 4 goes into 84 21 times. So you get kind of out of room here, but 21 and a quarter seconds. So as you can see, the time we're looking for, would it have been reasonable to guess that the time was going to be halfway between 5 and 50? That'd have been like, that would have been crazy, right? But it turns out it's not quite half. It's a little bit before halfway. Halfway between 5 and 55 would be what? 27 and a half. So it's yeah, there's no really easy peasy way to just intuitively know where that's going to occur. So anyway, it turns out it happened at about 21, well, at exactly 21 and a quarter seconds. Okay. Any questions at all on that stuff, guys? In the setup? Wow, we're thrilled to be here. That's good. Especially George and Aspen Tope. That's Monday, indeed.
Mm-hmm.
Let's do one more together, then you guys can have the rest of the class just to finish up anything you haven't finished. Or you can look at the practice quiz if you want. It's up on Classroom. What do you guys think? Should we do 15 or 16?
16.
We're do 16? Sure.
Okay.
Just a quick comment. This question, of course, is kind of similar to number 14. What process do you need to use on 14? Or what rule do you need to use on 14? The quotient rule, yeah. They're giving you a position function, and you're being asked to figure out the velocity function, so you have to take the derivative, and that function can't be simplified in any way that makes it easier to take the derivative, so you have to use a quotient rule. So 16. That looks kind of gross, right?
Yes.
Should we use the quotient rule on it?
Yes, you could.
You could. Yeah, you certainly could. Maybe to clarify the question. Is the quotient rule the most efficient approach you could take to take the derivative?
Probably not.
Like this?
No.
Also, let's clarify something again as well. They're giving us a velocity function, right? Velocity function. And they're asking us in part A to find the acceleration function. So of course, how do you find acceleration? It's the derivative of velocity. All right, so can anyone tell us how we can really, really simplify this? I do? What can I do?
Can you take put the square root of t and put it up as t to negative 1/2 in this chain instead?
You could, yeah, you could rewrite this as something like, in my opinion, this is not the simplest way to think about it, but that certainly is valid. 100% that's valid. By the way, let's flesh this out here. So, okay, so if you did that, what's t to the negative 1/2 times t to the positive 1/2?
Negative 1.
T to the, what do you do with the exponents?
Zero.
You add them, t to the 0. And then that times 1, of course, is itself. And what's t to the 0 power? 1. So that's a pretty good approach. I mean, if that makes a lot of sense to you, that's a good way to do it. What I was thinking of is just use the fact that, what if we find, we got 10 cookies and 30 something bananas or whatever, and you want to split it 2 ways. Like, this is how division works, right? This is the same as going 10 divided by 2 plus 30 divided by 2. That's the same thing, right? So I can do this. The principle holds here.
It's basically 1 plus 1 over root t.
Exactly, yeah. So I can rewrite this as, so it's root t over root t plus 1 over root t. And then this, of course, is, as long as t isn't 0, which we know it can't be because it says right here in the problem that t must be greater than or equal to 1. So this is just 1. And this, of course, this is where I would like probably to write it as t to the negative 1/2 power. So as you can see, well, Ave's approach gets us the exact same function. So 100% valid. All right, are there any questions on that that algebra stuff there?
Mm-mm.
All right. Acceleration is just the derivative of velocity. That's a big concept. Make sure you understand that one. So let's take the derivative of this. It's the derivative of 1. 0. Derivative of t to the negative 1/2 is
No?
negative 1/2 t to the negative 3/2 power. Now I could rewrite this if I want as, that looks pretty ugly, right? It's not the prettiest form. This 1's on top, so I can maybe say it's negative 1 over 2 times the square root of t cubed, something like that. That looks a little bit nicer. Is everyone okay with how I'm getting from this to this?
Mm-hmm.
Yes? Okay, find the particle's velocity and acceleration. So this is part A. There you go, we got it. Part B, what's the velocity and acceleration at time 4? So let's do, velocity first, I guess. Let's see, tricky or not so tricky to get this? I would say not so tricky. You just have to plug it into this function. So plug that in. And you get 2 plus 1 over 2. And let's get acceleration. Just plug in 4 here. So negative 1 over, we know this one, what's 4 cubed square rooted is what number? Is 8. It might be easier if you think about going square root then cube, or maybe you just know, 4 cubed is not too hard, right? 4 times 4 times 4 is 64. Square root of 64 is 8. So what we have is negative 1/16 for our acceleration. Again, if we're thinking about what would the units be here, this would be like units per second, and this would be units per second, or units per second squared. Okay, time for the interesting question. Sorry, this is all stuff that, if you want to be fluent in math, it's all stuff you got to know how to do. It's not the most exciting part. What I think is a really interesting question here is to look at C, which we actually didn't really need any calculus to answer C. Does anyone think they could give a good answer to C, a good complete answer? Anyone feeling brave? Kate? Just one?
Just one. As t approaches infinity, the velocity approaches 1.
Very good. That's true. True. I wouldn't say that's the full description, but yeah, definitely that's correct. I totally agree with you. You're leaving a lot to the reader to read into. Very professorial answer there. So good job. Desi, can you add to that?
I don't know. I was gonna say that.
Okay. Do you guys see what Kate's saying though?
Kind of like if you graphed it, what it looks like, or like what the graph is describing, I guess.
I'm not trying to say Kate's answer is really good, but just you could maybe elaborate more to help someone who doesn't find that obvious, right? So
Well, I don't find that
Okay,
obvious. You elaborate.
right. So
As T gets really big, as the time goes on and the amount of time gets bigger and bigger, the velocity function is going to equal 1 plus a very small number because it's.
Oh, okay, I get that now.
oh yeah, looking at this one.
Yeah, now I get that.
Yeah.
Or
So
you can look at the other one too and understand that it's going to be time, or it's going to be, square root of time over square root of time, which is 1, plus the 1 over a very big number, so it's going to be 1 plus a tiny number, so it's going to be almost 1.
yeah, exactly. Yes, that's a good explanation. So yeah. So if we wanted to be really precise, we could say something like the limit as time approaches infinity of the velocity function is 1. Now that goes hand in hand. I was thinking we could also add some other stuff. What does that mean about the acceleration then? What's happening to the acceleration is approaching 0. So these two statements really go hand in hand. Now this could be any number. Does it make sense how if this was a 2, this would still be a 0? So if you're basically, so is this particle, so some of your questions on this, the end behavior is going to be the particle is slowing down and slowing down. But that's not the case here. In this case, the particle is approaching a constant speed. So he starts off going, right, at some, what is his initial speed, by the way? When t is 1? 2. Very good. So if you look at his velocity function, velocity versus time, it starts off, well, it doesn't start until time hits 1, technically. So he starts off at 2 units per second, and then what does he approach in the long run? 1. So a good example of a horizontal asymptote. This is what the velocity function is doing. And so what's happening is this guy starts off with changing speed, but in the long run, he's approaching a constant velocity behavior. So there you go. So basically what we're looking for is something about how the velocity is approaching 1 and the acceleration is approaching 0. I think even, if you want to be extra awesome, his position function would therefore be approximately blank in the long run. Anyone?
Oh, sorry. Repeat that.
So for question C, we could also say, in the long run, his position function is approximately linear. That's what I was looking for. Linear. Because if you have a constant velocity, then your position function is linear. So. Okay. Well, take the rest of the class and just let me know if you have questions that you didn't want to ask in front of everyone. If you want to ask them to me individually, that's fine. I'll try my best to answer them for you.